All right, not everyone's here, but let's go ahead and get started. So a very brief review of last time, mostly of the bipartite expander thing. So last time, what did we do?
So Max, just one thing maybe before we start, just some logistical
Oh, sure, yeah.
comment. So just a reminder that homework 1 is due next Monday, and we put on the website the grade scope code, so you can go in there and submit when you're done. And again, a reminder, you can do it either individually or in pairs, and we encourage you to do it in pairs. And if you need to find like another student and you don't know anybody, you can use Piazza for that. That's an option for that. Now, next, also, I don't know, it's just me, but the resolution on what you write is very low, so it's hard to read.
Huh, really?
Yeah, I was gonna say the same.
That's weird.
Yeah.
The resolution is low. Why do I have so many technological issues? Let me retry doing the share, I guess.
Yeah, it seems like the pixel size is like, I don't know, huge.
That's bizarre.
Yeah. Oh, this is better. That's much better.
Wait, okay, but does it become worse when I do this? Does it become worse? Oh. Sorry, having trouble. Trying to make it smaller so I can see notes. Is it now worse again?
No.
No. Okay, good.
Do you want to try and write something just to see if it stays good?
Yeah.
Or now it started to deteriorate.
Really? So this is now hard to see.
It's better than before, but it's worse than it was. So, yeah, it's in between.
All right, let me try one more thing, and then we'll just give up on me being able to see my notes, because apparently it's really difficult. Okay, if I write now, can you see the scribble or not?
Yeah.
That's good. Another pixel size is back to normal. Yeah, the resolution is good.
Okay. All right. I'm totally bemused by however this works, but
apparently Zoom really doesn't want you to use a note at the same time.
Yeah, I don't understand. Anyway, let's get started. Hopefully that's the only technological errors we have. Okay, so what did we actually do last time? Well, Shahar showed kind of an application or connections between bipartite vertex expanders and kind of building what we were calling super concentrators, which were connected to like lower bounds in linear algebra, building kind of sparse super concentrators. I'm not going to talk about the lower bounds in linear algebra or super concentrators or review this, but I do want to review bipartite expanders, because we'll be using this. This lecture will be another application of bipartite vertex expanders. So as a reminder, what is a bipartite vertex expander? So I should say bipartite graph GLRE, let's say maybe let's say an NME bipartite graph. So the left-hand side has n vertices, the right-hand side has m vertices, and it's E-regular. And we'll say in a bit why I'm using E instead of D. Is alpha beta vertex expanding, or I'll just say expanding, if kind of for all small enough sets on the left-hand side, they expand outwards to the right-hand side in terms of kind of vertex expansion. So a little bit more formally, if for all subsets of L, such that the size of S is less than or equal to alpha times n, we have that the size of the neighborhood of S is at least beta times the size of S. So it expands out by beta times its own size. This is a vertex notion of expansion. We're looking at the neighborhood, kind of the neighborhood that is adjacent to small enough sets on the left-hand side. Last time we saw how this could be used to build kind of these super concentrators, these really connected, kind of specially connected circuits, more or less. This time we're going to see an application to error correcting codes, which I'll talk about in a bit. So I guess I want to note kind of one more thing that we discussed and a slight modification of it. So Shahar actually proved kind of probabilistically the existence of certain bipartite vertex expanders, right? And in particular, Shahar proved that kind of there exists some constant degree such that for all large enough n, there exist n 3n over 4, I think was the parameter, e 1/2 expanding bipartite graphs. And this was proved by the probabilistic method, right? We just kind of picked a random bipartite graph with these parameters, and we showed that probably it is indeed kind of a 1/2 vertex expander. The proof is the probabilistic method. And today we're actually going to use a slight variant of this claim, where all I'm going to do is I'm going to change 1/2 to 1/10e beta for some beta strictly greater than 3e over 4. So we're going to need a slightly different kind of regime of bipartite expanders. What's the proof? Well, you still use the probabilistic method, but it's a little bit more complicated and will be on your homework. So the proof is homework of the new version. But we'll be using it today for our application.
Let me just say one thing about the parameters here. I mean, there's so many parameters here going around. This gives them intuition.
Sure.
So think of n and m as very big. And m is something linear in n. So in all these applications, m is linear in n. And the degree e, so this is like the left degree is constant. So that's same in everything. And the question is how much we want these graphs to expand. So think about that. Ideally, that since every node on the left has degree e, is going to see e neighbors on the right. So the best possible expansion you can get is beta equal to e. Right? That's the best one. And also notice that because we want this for every set of size smaller than alpha, we have alpha times beta being at most 1, right? Because if a set of size alpha and expands by a factor of beta, it can't be more than m. So if m is at most n, then alpha times beta is at most 1, or in fact in this application at most 3/4. So we have two constraints. Beta is at most e, that's one constraint, and alpha times beta is at most, that's a constant, that's a 1. And these two applications need two regimes of parameters. So the first application that I showed you last time really needed both alpha and beta to be a constant. So actually what we wanted is beta to be 1 and alpha just to be some constant and half dwarf. And the application that Next is going to show today really needs beta to be really, really big, really close to maximal, which is e, but we don't care if alpha is less than a constant, like 1/10e or something like that. So somehow it's a different, so although e is a constant here, so then everything is a constant, the dependence of beta on e really is crucial for this application.
Yeah, we'll see kind of two thresholds, e over 2 and 3e over 4, that are kind of very crucial for these applications in error correcting codes. Yeah, okay, thanks, Shahar. So I guess maybe I'll pause and ask any questions about this before. So this will be the end of review from last time / talking about the existence of these expanders. Any questions before we move on to today's topic?
Cool. Maybe let's add one more comment. So sure. Let's say you think of this is something I think we also discussed last time. So this proof is probabilistic, but what if you actually want to construct this, graphs? Because if you want to design a code, you need to construct them. Well, it turns out that if you use, let's say, m equal to n or m close to n, then you can use sort of the standard expanded graphs we've seen so far with edge expansion and spectral expansion to get this to work really well for beta up to E over 2. So if beta is at most E over 2, then you can prove that you can get this to work. So you can relate edge expansion to vertex expansion and use a factor of 2. And to bypass this factor of E over 2, you really need different techniques. So the constructions of this graph, the explicit ones, don't look like the algebraic constructions that we briefly discussed and we're going to see more next week. They're going to look 2 weeks. They have to be very, very different. And again, it's a big mystery. Could you use algebraic constructions to design this graph so beta is more than E over 2? And some of the threshold of E over 2 turns out to be important not just for this application, but for many applications. So and you'll understand why later.
Yeah, E over 2, it'll be clear why. But mostly the reason is that if something's greater than E over 2 and you multiply it by 2, it's greater than E. It seems to be the important the important thing.
Yeah, I mean, there's also this notion of unique neighbor expanders, but
right, it implies a unique neighbor. We'll see that this is useful. Yeah. Okay, so today we're going to be talking about an application to error correcting codes. So I want to start by giving a little bit of motivation and background on error correcting codes before kind of diving into building them using expander graphs, which will be kind of our main focus today. So kind of what's the motivation? Well, I think classically, we kind of consider this a scenario where there are two people. Often they're named Alice and Bob. And Alice has some message, which is maybe think about as a k-bit string that she would like to send over to Bob. And the problem is that so Alice and Bob aren't sitting in the same room talking. Alice only kind of has access to send things to Bob through some kind of noisy medium, through some kind of noisy channel. And there are lots of different ways to define a noisy channel in practice, and they lead to different kind of theories of codes. But for now, think about maybe, if Alice sends a message of length n over the channel, we expect kind of like maybe a constant fraction of the bits are going to end up being flipped because of noise. So maybe it flips things independently with probability p. Maybe there's some adversary who's allowed to corrupt some constant fraction of the message. We won't care too much about what the model is, but think about kind of a constant fraction of what goes through this channel ends up getting, the bits end up getting flipped somehow. And right, this is actually a very realistic scenario. As I'm talking to you right now, probably packets are getting dropped, things are getting corrupted as it goes through, servers, routers, et cetera. And these things actually use what are called error correcting codes to make sure that you're able to hear what I'm saying correctly. Okay, so anyway, what's the goal here? Well, Alice would like to send the message M to Bob, but there's a problem because the message will get corrupted when she sends it through the channel. So what can she do? Well, the kind of natural thing to consider is that we would like to, Alice will encode M into some larger space. So she'll kind of add redundancy so that even if things get corrupted, there's some hope that Bob will be able to figure out, due to this kind of extra redundancy that she added, what the original message was. So E is some encoding function, and it goes from it maps messages that Alice would want to send, k-bit strings, into some larger space, 0, 1 to the n, where n is greater than k. And so on the other end, she'll send this encoded message through the noisy channel, and Bob will receive some version of it that is, somewhat corrupted. We'll call it EM prime. And ahead of time, kind of Alice and Bob have agreed on the encoding and decoding functions. And so Bob has some kind of decoding function that he will apply to the noisy version of the encoded message that he gets. So D here is now a function from 0, 1 to the n to 0, 1 to the k. And the hope, it's not at all obvious you can do this, but the hope is that kind of Alice and Bob have cleverly chosen their encoding and decoding functions so that most of the time, even if some constant fraction of the bits are flipped once Alice sends the encoded messages, that this will actually output the decoding function on the noisy version will actually output the original message. And Alice will have successfully sent M to Bob. So this is kind of the overall idea. This way of encoding things from k-dimensional space to n-dimensional space is called a code, and it's kind of the main object that we'll be talking about today. So before going into formal definitions, I want to give like a really basic example, like the most basic thing you could think of. So let's assume, and of course this is not a realistic assumption, but let's assume that the channel makes kind of at most one error. So it flips, Alice will send some message to the channel and it flips at most one bit. I'm just guaranteeing you, this isn't realistic, but just for the sake of looking at something simple, I guarantee you that it will flip at most one bit in the message. Kind of what I mean here is it flips at most one bit. So can anyone tell me what is kind of a naive strategy that Alice and Bob can use to send a message M if they know that only one bit will get flipped, so that 100% of the time, Bob will be able to figure out what the message is?
You could send it like 3 times and take the majority.
Yeah, exactly. Duplicate bits. Yeah, exactly. So this is kind of the most basic thing you can do. If you look at this, so there's another motivation for error correcting codes that's in terms of like data storage. So you kind of want to store your data such that if some hard drive gets scratched or there's some bug, you'll be able to recover the data. One simple way of doing this, right, is just store multiple copies of your data. It's called backing things up. We do it all the time. Well, hopefully you do it. So this basic kind of process of just repeating M 3 times if there's one error, this is called a repetition code. So repetition code. So in other words, Alice will map M to MMM. And then this will get sent through the noisy channel. And then the output, the key here is that because there's only one error, only one of the 3 M's can get corrupted. Right, so it outputs something that looks like M prime MM, say. It doesn't really matter where the corrupted one is. The point is that 2 of them are unaffected and 1 of them is corrupted. And this means that if Bob takes the majority of these 3 messages, he will always output the original message. Right, and okay, I picked kind of one error, but you could use this strategy for any finite number of errors, right? If I say, this channel will create T errors kind of no matter what you send, I can just repeat 2T plus 1 times, right? So there's kind of the T repetition code that sends M to T plus 1 copies, 2T plus 1 copies of M. And then the same thing happens, at least T plus 1 of them are good. So you take the majority of the output and you will always get M, right? So, okay, maybe the lecture's done. Have we solved coding theory for any number of any constant number of errors? I can build this code for you. What's the problem? Okay, this lecture has another hour. Obviously there's some kind of substantial issue with this. Well, notably, let's say we tried to go back to, I promised you that the channel was going to make some fixed number of errors, but this isn't really realistic. I told you at the beginning that you should think about the channel as making kind of a constant fraction of errors. Like if you send n bits through the channel, you expect maybe n over 6 of them to get corrupted. And the problem with this repetition code is that as I'm able to deal with more errors, I'm massively blowing up the size of the message that I send. So somehow this doesn't really work, right? Because as I blow up the message, I expect there to be more errors, but to deal with more errors, I have to blow up the size of the message. And this really ends up kind of, I'm not going to go into the exact details, but basically the repetition code, will only work for messages of size 2 or something if the channel is reasonably noisy. So kind of clearly this strategy does not work. And I'll go into in a minute kind of more formally what sort of properties we actually want to make sure that the code will work over kind of a constant fraction of errors. But I just want to point out the kind of, this code has issues. It's not actually going to work in practice for a number of reasons, including this one. Okay, that's kind of all of the motivation that I wanted to give before jumping into formal definitions for error correcting codes. So I want to pause to see if does anyone have questions on the motivation or kind of just the basic setup. I've been a little bit vague, but are there any questions about the kind of setup or motivation here? Okay, if not, then I will go ahead and define codes. And in particular, I'm going to define something called an NKD code, or NKD binary code. So all of our codes will be binary. In general, this doesn't have to be the case. You could encode things over 1 through Q, some kind of alphabet that's larger than 0, 1. We're just going to focus on the binary case for this lecture. And I guess before I give the definition, I want to note one more thing, which is that in kind of the motivation, I talked about kind of an encoding and a decoding step, right? Alice kind of starts with a k-bit string and she encodes it into some sort of n-bit string. Normally, kind of what encoding you use is fairly obvious. I'll maybe mention this a little bit later down the line, but for now, we're actually going to consider codes just to be kind of the encoded objects in 0, 1 to the n. So yes, in the back of our mind, we're thinking these are encodings of k-bit strings. This is some encoding of a k-bit string, but really I'm just going to be considering kind of subsets of 0, 1 to the n and their structure. And this is going to be what I call a code. So, okay, let's be a little bit more formal. So a subset of 0, 1 to the n is an NKD code if it satisfies the 2 following properties. So 1, it should be encoding, it should be some kind of encoding for k-bit message strings. And what do I need for this to be true? I just need that the size of C is 2 to the k. It needs to be able to be mapped to injectively by k-bit strings. So this kind of tells you what the k parameter is. And the second is that the minimum, and I'll define this in a sec, the minimum Hamming distance between pairs x, y, and c is d. So this is a parameter, d is a parameter called distance. Okay, so what is Hamming distance? I should probably tell you what this is. The Hamming distance of 2 vectors x, y is just the number of coordinates that they disagree on, right? So this is just kind of the number of I in n such that xi is not equal to yi. So just the number of coordinates on which they disagree. So what is the distance? This is where you're looking at the minimum of all pairs of all. So we call kind of elements of the code words. So you're looking across all pairs of code words and you're asking what are the closest 2 code words? This is the distance, called the distance of the code. And maybe let me just note another way to write Hamming distance. So there's a similar concept called Hamming weight. And this will be useful a bit later. And the Hamming weight of a vector x, it's denoted by these two lines on either side. This is just equal to the number of 1s in x. So it's like the support of x, the number of 1s. And so we can notice that we can write the Hamming distance as the number of 1s in x plus y, where this is mod 2. So maybe I want to write x or y. Right, so the number of 1s in x plus y is, so when is it 1? It's exactly 1 when the coordinates don't agree. So this is the number of coordinates where they differ. The Hamming weight of x plus y is another way to think of Hamming distance. Anyway, so these are our objects. They're subsets of 0, 1 to the n, which are of size 2 to the k, and have this distance property where every pair of code words is kind of at least at Hamming distance d apart. So let's go back to the repetition code and maybe examine kind of, what kind of code is this? So let's go back to our basic example. Let's look at the kind of t correcting repetition code. So this is where I repeated things 2t plus 1 times. And I claim it's not too hard to see that this is 2t plus 1 times k, right? So what's the size of n? We repeated k 2t plus 1 times, so n is 2t plus 1 times k. The size of the message length is some arbitrary k. And what's the distance? Well, so what I've done is repeated the string 2t plus 1 times. And so the closest to code words would be if I change the message, the original message, by 1 bit, right? And then the corresponding 2 code words would be, how far apart? Well, they differ by 1 in each of the 2t plus 1 repetitions. So I claim that the distance is 2t plus 1. And what I want to note is there seems to be some connection, right, between, so we said that this can correct t errors. There seems to be some connection between this distance parameter and the number of errors that can be corrected. Before I maybe go, so I'm about to claim that this is in fact a very general equivalence. It doesn't have to do with the repetition code. This is true for all NKD codes. But maybe let me pause and ask, this is kind of one of the main definitions for today and objects that we'll be working with. Are there questions with the definition or example here? If not, I'll go ahead and go into the claim that distance is kind of equivalent to number of errors that we can correct, the code can correct. So claim, let C be an NKD code. Let X be some vector in 0, 1 to the n, which we think of as a corrupted code word, in the sense that there exists some Y in the code such that so this is just the Hamming distance between X and Y, such that the Hamming distance between X and Y is strictly less than d over 2. Then Y is the unique code word closest to X, and namely can therefore be recovered from X. So if I give you such an X that's within d over 2 of some code word Y, I claim that Y is the only code word that is that close, and therefore if I just kind of brute force over all code words and look for the closest one, I can uniquely find Y. Kind of X should be thought of here as a corruption of Y. So in other words, kind of I can, we can recover Y from X. And I guess I'll just note that kind of further this is tight. We can't replace this with anything better than d over 2 if we're interested in uniquely getting Y back from the corrupted word X. Okay, so what's the proof of this? Well, this is also an exercise. But maybe let me give intuition for this, which is just kind of, what is distance saying about a code? It's really kind of saying that the code words are really spread out in 0, 1 to the n. A large distance means the code words are very spread out in 0, 1 to the n. And in particular, you can kind of imagine drawing balls of a certain radius around these code words. And the idea is kind of, if all of the balls are disjoint, if I only kind of corrupt one of these code words, by some small enough amount that it stays within the ball, I should be able to uniquely map it back to the center of that ball. So the idea here is just, if the code words are kind of largely spread out, we should be able to deal with many corruptions intuitively, because even if we corrupt it pretty far, it'll still stay reasonably close, at least with respect to all of the other code words, to the one that it started from. Okay, so informally, what does this say? It just says that basically distance is equivalent to number of errors that I can uniquely correct for. Okay. So now I want to ask, okay, I've defined a code. I've kind of dealt with the most obvious property. I've said, here's a characterization, kind of a combinatorial characterization of how many errors this code can correct. But maybe what are some kind of natural properties? What might we hope for in a code? What is kind of the best case scenario? So question. What do we want from a code? What do we want C to satisfy? Well, I claim that there are kind of 3 natural properties that you might want to consider. The first I was just talking about, right? We we said that there was some kind of problem with the repetition code because it didn't scale correctly. Kind of to deal with T errors, we had to kind of massively increase the size of the encoding, and that was going to cause more errors. And so somehow this didn't work out. So what you need is that kind of the number of errors that you can deal with should scale linearly with the size of the message, of the encoded message that you send, right? Because you expect a constant fraction of the message to get corrupted. So we better be able to deal with a constant fraction of errors. Otherwise, these things should scale linearly. So the distance, so one, property one, we'll call linear distance. And this just means that the distance d should be kind of, oh, that shouldn't be c, should be a constant fraction times n. So maybe the distance is n over 4 or n over 8. We won't really care about the constant. We just want it to scale linearly with n. This way, kind of as we scale things up. So like expanders, right? The way these things are formally defined is we would talk about kind of an infinite family of codes as n and k are going to infinity. And basically, we want the distance to be, scaling linearly with n as we look at this family of codes. Okay, the second thing that we might hope for is that we're sending messages. So remember the motivation is that we're sending messages of size k. And one would hope that kind of in order to do this, you wouldn't have to blow the size of the message up too much, right? So if our message size is originally k, what's the best that we can hope for? Hopefully we could do this by only increasing the size of our message by a constant factor, right? So one hope, and maybe you can call this space efficiency. I'll say another name for it in just a second, which is called constant rate. But the idea is that we want n to be kind of O of k. We don't want our encoded vector to be way, way bigger than our original message. Okay, so what is this maybe formally called in the literature if you go look? Well, another way to compare n and k is through their quotient, right? So kind of the natural property to look at is k over n. This is called the rate of the code. And an equivalent statement to saying that n is equal to O of k is that their quotient is a constant, is equal to O of 1. Or sorry, maybe I should say is equal to omega 1. So we want this to be a constant. This is the same thing as just saying we don't want n to be too much bigger than k. And the best we can possibly hope for asymptotically is that it's only a constant times bigger, right? This is the best we could possibly do. Okay, so these are two kind of combinatorial properties. The third property is that if I actually want to kind of use codes in practice, I need them to be somehow computationally efficient, right? This is 1 and 2 are kind of interesting mathematically, and they're very useful properties. But if I actually want to, use these error correcting codes, I need them to work fast, right? Like there's an error correcting code going on right now as I'm talking to you, and it needs to be in real time. These things need to be efficient to actually work. And it's also interesting, from a theoretical standpoint, kind of when you can build these things efficiently. So the third property is I kind of want things to be computationally efficient. And I'll kind of split this into two parts. So what does it mean for a code to be computationally efficient? I'll kind of split this into two parts. And one part we're going to more or less ignore. I'm going to kind of claim we get it for free in a second. And the other part will be kind of our main application of expanders today. So one of the parts, the first part, is I'm gonna remind you we kind of ignored for the time being the mapping that sends between messages of length k to encodings, right? But in practice, this actually needs to be done efficiently, right? We need to be able to map our k-bit message to a code word efficiently, or the whole process can't be efficient. And similarly, we need to be able to map a code word, like a real code word in the code, not a noisy one, back to the corresponding message. This also has to be able to be done efficiently. Right, so kind of one is moving between messages and code words should be efficient. And I'm going to kind of say in a second how we get this for free, how we can get this for free. And the second part, which is not for free, is that we also want this kind of decoding procedure that we were talking about here, right? Where you get a code word that's maybe been corrupted by the distance over 2 or something less than or equal to the distance over 2. and you want to find the closest associated code word actually in the code. You also want to be able to do this efficiently, right? So this is kind of every step of the error correcting algorithm. You encode it, we can do that efficiently. We get back the noisy version. We then efficiently find the closest code word to the noisy version, and then we map that back to the original message. And this gives the entire process. So as long as we also have kind of, I will call this maybe the noisy recovery or decoding, it's often called, is efficient. So notice that if we have all of these properties, so property 1 says we can deal with channels that have a constant fraction of errors. So that's great. The second property basically says it's, you know, it's space efficient. Kind of as you scale up, you're only going to be sending a constant fraction more bits than your original message. So things are kind of efficient in that sense, space efficient in that sense. And third, things are actually computationally efficient. I can, you know, maybe I can hope to do this in real time. I can actually apply this in practice. And we'll see that getting all 3 of these is really hard, but we will show how to get all of them using expander graphs. So we'll basically show how to build codes out of expander graphs that do all of this. So I quickly want to talk about this computational efficiency thing a little bit more. In particular, I want to introduce something called linear codes before we move to the expander part. And what's the idea here? Well, working with this computationally efficient definition at the moment is a little bit difficult, because so far what we've defined are like purely combinatorial objects, right? They have kind of no structure. They're just very spread out point sets in 0, 1 to the n, right? This is all they are so far. And having any kind of efficient structure with them is difficult to do, right? Generally, these type of combinatorial problems are NP hard. There's often nothing we can do kind of better than brute force. And so how do we get around this? Well, we're going to restrict our codes a little bit. We're going to force our codes to have kind of nice structure. Kind of the natural thing to enforce is linearity. And kind of this will let us build codes out of linear algebra. And this is kind of the most commonly studied subset of codes. So this is called a linear code. And I'm just going to define these for you and then make 2 claims about them. And then we'll move on to the expander codes, which are a subset of linear codes. So linear codes. A linear code, so we say maybe an NKD code C is linear if C is a subspace of F2 to the n, like a sub-vector space of F2 to the n, is a k-dimensional subspace. And what does this mean practically? Well, I'm just enforcing the requirement that for all C prime in C, I'm enforcing that their sum is also in C. Their sum mod 2 is also in C. This is all that linearity is doing. I'm enforcing this kind of structure in the code that it has to be closed under addition. That's all I'm doing. And you know, certainly these things exist by basic linear algebra, right? We have subspaces of every dimension. And there are kind of 2 nice things that I want to note about linear codes before I move on. I'm going to leave them both as exercises. So the first claim is that kind of linear codes give kind of efficient encoding and decoding between messages and code words, not between the noisy version of the code word and the closest one, but just moving from the message space to code words and back and forth. This can be done efficiently if your code is linear. And this is kind of why I ignored it in the beginning. We generally don't think about this because it's easy to do with these linear codes. This is just from messages to code words and back. And the reason for this, I'm not going to go too much into, but basically it turns out that you can move between messages and code words by multiplying by a matrix that kind of corresponds to the subspace called a generator matrix. So basically kind of the code word associated to X will just be X applied to this matrix. And so this is efficient and easy to do. If you want to know more about it, if you just look at kind of any introductory lecture notes for error correcting codes, this will be there. So if you're interested, just you know, Google it online. The second claim is that there's a really nice characterization of distance for linear codes. So in particular, the distance of a linear code is the minimum Hamming weight. Is the minimum Hamming weights across all code words. Right, so instead of looking at pairs and looking at the closest, the minimum distance between pairs, we can instead look across just code words and look at kind of which code word has the fewest ones. This will be an equivalent characterization of distance when we're in the linear case. And
Non-zero code word.
Sorry?
A non-zero code word.
Yes, thank you. Non-zero code word. And actually, to prove this, it's important that the zero code word exists in the code, which it always will when we're forcing it to be a subspace, right? Yeah, thank you. C, let's say C without zero. Thanks. Okay, so that's all. That's actually all I wanted to say about linear codes before we move on to expander codes. Are there questions on definition of codes? I've been somewhat vague about linear codes, but at least the definition before we move on to defining codes through expanders. Okay, great. So, okay, the main idea for the rest of lecture will be that we are going to kind of take bipartite graphs that are expanding, and we're going to use them to define a code, and we're going to prove that this code has all of the desirable properties that we laid out before for a good code. So before I kind of do this explicitly for expanding bipartite graphs, I want to talk about, I need to define for you what is the code associated to some generic bipartite graph. So let's look at that first. So kind of let G LRE be an NME bipartite graph. And let's define the unnormalized adjacency matrix, or let's notate it rather. Adjacency matrix by, let's say, MG. So this is just the n by m matrix that measures the edges between the left and the right hand side. We'll come back to that in a second. So the code, which we'll maybe call CG, associated to G, is just defined to be the kernel of the adjacency matrix, of the unnormalized adjacency matrix. So this is a linear code, right? Because basic linear algebra exercise is that the kernel is a subspace, is a linear subspace. So just kind of immediately by definition, this is a linear code. It's not clear that it has any good properties beyond that, but it is some subspace. Let me maybe write out, I want to give kind of a few ways to visualize or think about this code, because just kind of telling you it's the kernel, at least to me, is not very intuitive. So let's write out a little bit more explicitly what this means. So by the way, I should say that this is the left kernel of MG. And what I mean by that is that this code will consist of all vectors in F2 to the n such that xmg is equal to 0. Okay, and kind of what does that mean a little bit more explicitly in matrix form? So we have mg over here, right? We have this n by m matrix. What I'm saying is that a vector x is in the code if this product is all zeros. And one way to think about this is that each column in the adjacency matrix, so this is, has some columns. Maybe let's kind of just write in some column to 1, just kind of arbitrary. Each column can be thought of as a linear constraint. Why? Well, what is it saying that the product of x and mg is all zeros? It's saying for every column, for each column ci, I'm enforcing the following constraint on the code. I'm enforcing that their inner product is equal to 0, right? This is just from the definition of matrix multiplication. So you can think of each column in this matrix as a linear constraint on the code. And a code word is in the code. A vector is in the code if it satisfies all m of these constraints given by the columns. Okay, so this would be true of kind of any matrix, right? This doesn't say anything about coming from a bipartite graph. So why are we talking about coming from bipartite graphs? Well, let me now give another view of this code, which is actually through looking at the bipartite graph and is a little bit more visual. And kind of this is actually the view that we'll be using for the rest of the lecture. These are all equivalent views, but it's nice to have multiple ways to think about these things. So let's draw out the bipartite graph. So we have m vertices over here on the left. We have m on the right hand side. We have m vertices. And remember, so basically each of these vertices on the right hand side corresponds to some column in the adjacency matrix, straight just by definition. And so it turns out that basically we can think of each of these, like I was talking about the columns, each of these can be thought of as a constraint. So we'll kind of think of the right hand side of the bipartite graph as the constraints of the code. And on the other hand, on the left-hand side, we'll think of this basically as kind of potential inputs. So basically this is there are n vertices, and so a vector in f2 to the n gives a labeling of L, right? So some vector in f2 to the n, 0, 1, 1, 1, 0, 0, 1, 1, 1, 0. This gives some labeling to L. And we can look at the structure of this graph and we can use it to determine kind of, is this input in the code? And if not, how many columns is it violating? How many constraints is it violating? And so how do we look at this? Well, so kind of a little bit more formally tying things back to the matrix version, what exactly is a constraint over here? So let's maybe actually add in some edges to this graph. So let's say that this top, let's say that this first constraint over on the right is connected to the top 3 vertices on the left, and we want to ask if this constraint is satisfied, right? So this would be like if this would correspond to the matrix case if I had 1, 1, 1, and then kind of all zeros. So this would be the equivalence in the adjacency matrix and just how I'm drawing out the bipartite graph. And so what do I want to check? Well, the constraint, right, is that the inner product of x with this column is 0. And so what does this mean? Well, this is equivalent to just looking at all the neighbors. So we want to look at the neighbors of V, and we kind of want to sum over the neighbors of V. So let's say that this is kind of x, and and this is the labeling. Maybe let's say kind of the coordinates I are neighbors. So these are coordinates 1, 2, and 3. Right, so coordinates 1, 2, and 3. And so we're going to be basically summing over xi for the neighbors. So we're just going to be looking at the neighbors on the left-hand side, and we're going to be summing over mod 2 their labeling. So what do we get here? We get 0 plus 1 plus 1. And mod 2, this is 0, which is what we want, right? We said that this inner product over here has to be 0 for the constraint to be satisfied. So this constraint is satisfied. But let's say we maybe look lower down in the graph, and we have, say, these edges. So now when we look at the sum of the neighbors of this constraint here, maybe the ith constraint, we get kind of 1 plus 0 is equal to 1 mod 2. So this means the constraint given by the ith column of the adjacency matrix is not satisfied. So if we have this structure in the graph, this implies that there's a violated constraint, and therefore kind of this labeling is not in the code. Right, so these are kind of 3 equivalent ways to look at the code defined by a bipartite graph, and we'll mostly be using kind of this graphical view for the rest. So this is kind of an important definition. So I want to pause again for questions before moving on. We're now going to kind of look at this, and we're going to prove that it satisfies all of our nice properties, so long as the graph is a good expander. But first, questions maybe on the definition. I think the first time you see this, it can be a little bit confusing.
So where exactly do you get like the edges from? Like, where is the information in like the matrix that tells you which edges are
Well, just if this is indexed by L, right? The left-hand side is indexed by. So think of first having a graph and then having a matrix. This is just the adjacency matrix, right? So if there's an edge between a vertex and a vertex and R, you write a 1.
Yeah.
Okay, I kind of went from first from the matrix over to the graph, but this is just the adjacency matrix of the graph. Think about it as we start with the graph,
right?
And then the code is defined through the kernel of the adjacency matrix, but kind of you can still just think about it in graph form. You don't really have to worry about the adjacency matrix.
Yeah. Sorry.
No problem. Okay, cool. If there are no more questions, let's go ahead and kind of look at our 3 properties. And actually, I just want to start by analyzing the rate, kind of right off the bat. So remember, the rate is kind of k over n. It's the dimension of the subspace divided by kind of the total dimension by n. So what is the dimension of the subspace here? What's the dimension of the code? Well, the key thing here is that MG is an n by m matrix. And basic linear algebra says the rank of this matrix, n is greater than m. So the rank of this matrix is at most m, and therefore the dimension of the kernel is greater than or equal to n minus m, right? So this means that the dimension of kernel of MG, which is the k for the code, that this is greater than or equal to n minus m. So as long as we pick m to be kind of reasonably small, like any constant fraction times n. So let's think of m as being like 3n over 4 or something, right? Then this implies that this is greater than or equal to n over 4. And so what's the rate? Well, this implies that the rate, which is k over n, is greater than or equal to n over 4 over n, which is 1/4. So in other words, I don't have to use expansion properties at all. One nice thing about defining codes in this way is as long as I don't put too many constraints on the code, right? So you can think of kind of the more constraints I put on the code, the worse the rate is going to be. But as long as I kind of only put a constant fraction of constraints on the code, I am going to have constant rate just by basic linear algebra. It has nothing to do with expansion properties. So the rate is really easy to analyze. We don't have to use anything beyond the definition of the code. The second 2 properties, kind of distance and computational efficiency, are a little bit more difficult and will require expansion. So let's kind of start with distance. So remember that we want linear distance. We want some distance that's like some constant times n. That's our goal. And I claim that we kind of will indeed get this as long as the associated bipartite graph is a sufficiently strong expander. So in particular, let's say that G LRE is an NME alpha beta expanding bipartite graph where beta is strictly greater than E over 2. So this is going to be the threshold that Shahar was talking about. We're going to see for lots of applications, being greater than E over 2 is important. Then the distance of CG, of the code associated to G, as we just defined it, is strictly greater than alpha times n, whereas alpha is the first of the 2 expansion parameters. So in other words, for kind of constant alpha, we do indeed get linear distance. And how does one prove this? So this is, unsurprisingly going to be proved through our expansion property. Okay, so first of all, I'm going to use kind of our nice characterization of distance for linear codes. So remember I said, because we define this as the kernel, we get kind of linearity for free. So this is a linear code. CG is a linear code. And this means that the distance, recall the distance of CG is the minimum Hamming distance of non-zero code words. Is the minimum, sorry, Hamming weight. Hamming weight of non-zero code words. So in particular, it's enough to prove the following. It's enough to show that if the Hamming weight of X is less than or equal to alpha n, some constraint is violated. In other words, X does not lie in the code.
Or X is all 0.
Or X is all 0. Yeah, thank you. So maybe I should say between 1 and alpha n. So this is enough to prove the distance by this characterization. So let's see, how do we prove this? How do we prove that for kind of small x, small support x, some constraint is violated? Well, let me just go back to kind of the bipartite version over here. And let me just note that I called X kind of a labeling of the left-hand side, but you can also think about it just as a subset, right? For every vertex in L labeled 1, we think about it as being in X. If it's labeled 0, we think about it as not being in X. So this defines a subset on L. And we'll use this to talk about kind of expansion related to the code word, or to the potential code word. Okay, so what's kind of the key idea? The key idea will be something that Shahar actually mentioned at the beginning of the class called a unique neighbor. So the key will be to show that X has a unique neighbor, and I'll define what this is. This is just a vertex on the right-hand side. So in other words, a constraint that's adjacent to exactly one element or coordinate of X. So why is it enough to prove this? Well, if we have a constraint, remember that the way the constraints work is we sum over all of their neighbors mod 2. So if the constraint is only adjacent to one element of X, its sum mod 2 is 1, right? Because it has one thing that's 1 and everything else is 0. So its sum mod 2 is 1 and therefore it's violated. So if we can prove that kind of all X with small support have a unique neighbor, it implies there must be a violated coordinate. Okay, so how do we prove this? This follows actually almost immediately from the expansion property. So why is this the case? Well, notice that kind of by our assumption on the size of X, we can bound the size of the neighborhood of X, right? In particular, the size of the neighborhood of X by our expansion property is greater than or equal to beta times the size of X. And we've said that this is strictly greater than E over 2 times X. So let's now assume that maybe there are no unique neighbors. And what does this mean? That means that everything on the right-hand side is hit by at least 2 edges, right? So if there are no unique neighbors, I'm just going to call them UN. If there are no unique neighbors, this implies that there are strictly greater than E times X edges, because there are E over 2 times X neighbors, and all of them have to be hit twice if there's no unique neighbors. So this implies that there are greater than EX edges coming out of X. But this is a contradiction, right? Because our bipartite graph is irregular. There are exactly, in fact, EX edges coming out, E the size times the size of X edges coming out of X. And I've just said there have to be greater than that many by the expansion property. So this is a contradiction, and our initial assumption must have been, false. So there has to be a unique neighbor, and a unique neighbor implies a violated constraint. And so we're actually done, right? This gives a contradiction. And that completes the proof. There has to be a unique neighbor if the support of X is small. And that implies there's a violated constraint. So other than the all zeros vector, there is no vector in the code. There is no code word that has less than or equal to alpha times n ones. And because the distance is equivalent to kind of the minimal Hamming weight code word, this bounds the distance to be linear as we desire. Okay, any questions about this proof before we move on to the efficient decoding? So I guess maybe it's worth noting kind of, we mentioned that this E over 2 thing is really important. It is often for this reason that kind of it forces there to always be a unique neighbor. This is another version of expansion called like unique neighbor expanders that you can look at. And these are often useful for getting exactly this type of structure. Okay, so let's move on to the decoding algorithm then, which I think we should kind of just have time to go through. So to efficient decoding. Okay, so I want to talk about this maybe a little bit morally first before I go in and formally state the theorem. The idea, remember, is that we're kind of given, some x in f2 to the n. That's a corruption of some code word y that's actually in the code. And the idea is that we want to, as long as x is kind of close enough to y by some linear, only off by some linear number of coordinates, maybe less than alpha n over 2 is in particular what we'll see. So maybe I should say kind of x minus y is less than or equal to alpha n over 2. What we want to be able to do is to kind of find the closest code word y. So in other words, find y efficiently. So what's the naive way to find y? Well, you can just brute force over all code words and find the closest one to x. And this has to be y by kind of definition of the, or I guess by the claim we had about distance before, that y can be uniquely recovered from x. So you could do it by brute force, but this is exponential time. And the question is, how can you do this in polynomial time? How can you do this efficiently? It's not always clear. And we'll show that kind of because of expansion properties, it turns out that a very simple local kind of iterative algorithm will succeed in this. And I kind of want to just pictorially draw out the algorithm before starting. So the idea is that we'll kind of start with the labeling given by x on the left-hand side. So, I don't know, let me just draw in something. And then on the right, we'll have the constraints. And the idea will be basically we will go through x kind of coordinate by coordinate. We'll try to correct x locally by coordinate. And what I mean by this is let's maybe focus on some coordinate in here, and let's say for simplicity that e is 3. Just for this example. The idea here is, I'm not going to draw on the rest of the edges, but let's say that 2 of these constraints are violated, and one of them is correct. In general, I'm going to look for a coordinate where the majority of constraints are violated. What happens when I flip 0 to 1? Right? What happens is that all of these sum mod 2 that it's connected to on the right-hand side, all of them flip by 1, right? Because what I'm doing is I'm changing something from a 1 to a 0 or a 0 to a 1, and I'm only changing one of them. So all of the sums shift by 1. So, this sum now goes to 0, this sum now goes to 0, and this sum now goes to 1. So what do we see? Well, we've gone from 2 violated constraints and 1 satisfied constraint to 2 satisfied constraints and 1 violated constraint. So in other words, this is some very simple method where, if there exists a coordinate where the majority of constraints touching that coordinate are violated, if we flip the value of that coordinate, we will always lower the total number of unsatisfied constraints, right? Because the majority used to be unsatisfied, and I'm flipping it. So now by definition, kind of the strict majority is satisfied. So when I apply this local procedure, and the algorithm that we're going to be talking about is kind of just doing this again and again. I start with x, I look for a coordinate where the majority of its constraints are violated. I flip that coordinate, and I just repeat this process, until there are no coordinates that have a majority of violated constraints. And there are kind of 2 things to notice about this algorithm. One is that in each round, you always reduce the number of violated constraints. So this means that, and I'll write this all out formally in a second. I just kind of want to get the intuition first. This means that this algorithm has to terminate at a linear number of steps, right? Because there are only m constraints. And if I get better every step, there can be at most m steps, right? So kind of no matter what, whether or not this algorithm actually works, it will terminate in O of n steps. So kind of this algorithm is efficient. I don't have to worry about the efficiency so much. I just have to worry about when I end, after doing all of these local flips, I actually end up at y. That's what we need to prove, right? So maybe let me now write out the algorithm a little bit more formally. We'll call it iterated decode. And it'll take in some x, which is close to y, and we hope that it will output the associated vector y, but I won't prove this yet. So let's say that so at each step, we're going to flip one bit. Let's say that xt, for now, x0, will be kind of the vector that we're working with at the tth step after all of the flips that we've done at the previous steps. And the idea is that this is just a simple while loop, right? It basically just says kind of while there exists a coordinate of xt with kind of majority violated constraints. And there's a mathematical way to write this in terms of the adjacency matrix, but I think kind of the pictorial way is a little bit more intuitive. If you want to see the mathematical way, you can look in the notes, it's written there. With the majority of violated constraints, so maybe say coordinate I, with violated constraints, we will flip I. In other words, we will set xt plus 1 to be equal to xt plus the standard basis vector ei. Right, so this is just exactly what I said before. We're looking for a coordinate that has majority violated constraints. And if we find one, we're flipping it. If not, we're done. We output, else, I guess we just output xt, which we hope is y, and we will prove as long as your graph is sufficiently expanding that this is indeed y. So any questions about the form of this algorithm before we prove that you do indeed get y? Okay. So let's can you see what I'm writing, by the way? G, I modified something. It's still showing up.
Yeah.
Okay, thanks. So let GLRE be an N M E of alpha beta expanding bipartite graph with beta strictly greater than 3e over 4. So last time for distance, we only needed e over 2. Now we're going to need something even stronger. We need 3e over 4. But as I claimed in the beginning of the class, these types of expanders do still exist, at least through random constructions. So we need some kind of very strong beta, but we're going to be okay with alpha being a little bit smaller. We're not going to worry about alpha for now. Okay, so then let x be kind of a corrupted code word. So let x be some vector in f2 to the n, such that there exists y in the code associated to g in CG, where x is not too far from y. So the Hamming distance of x and y is less than or equal to alpha n over 2. So it can be kind of linear. This is still linearly far away from y. So we're still going to be kind of able to efficiently correct up to a linear number of errors, which was our original goal. We'll be able to do this efficiently. Then I claim that iterated decoding of x is always equal to y. And moreover, I already kind of mentioned why this is true, but it terminates in O of n kind of rounds. Right. This is obvious because it decreases the number of satisfied constraints in every round, and so it has to terminate in at least or in at most m rounds. So this part is kind of trivial by definition. So we'll mostly be focusing on the fact that when the algorithm terminates, it does indeed output the y vector that's close to x. Okay, let's go ahead and prove this. This is the last thing we'll do today. Okay, so like we did in the algorithm, let's let xt kind of be the, for a step b, kind of be the current vector after all the flips that we've applied to it. So x0 is x, right? X0 is equal to x. And let's let et, let's let this be kind of the corrupted coordinates of xt. So in other words, et is going to be the coordinates where xt differs from y, right? If there are no corrupted coordinates, then x is equal to y, and we're done because y is a code word. So this will be coordinates in 1 through n such that xti is not equal to yi. So these are the corrupted coordinates. And kind of our goal. So what do we want to prove? We want to show that if et is non-empty, right? If there exists a corrupted coordinate, so if the size of et is strictly greater than 0, then we want to prove the algorithm doesn't terminate, right? So this is equivalent to saying that when the algorithm terminates, it has to be at y. We're saying that if it's not at y, we will prove the algorithm does not terminate. So we're just proving the contrapositive. So what does it mean for the algorithm not to terminate? Well, the algorithm terminates, if and only if there isn't a coordinate which has majority violated constraints. So we want to prove that if the size of et is greater than 0, then there exists a coordinate I with kind of the majority of its constraints violated. Okay, and how are we going to prove this? Well, we're going to prove this by okay, let's fix some t, and we're going to look at kind of the neighborhood of et, and we're going to break. So let's look at it. We'll examine kind of the neighborhood of et. Actually, okay, sorry. First, I guess I want to say we're going to do this in 2 steps. We're going to make an assumption first. So we're already assuming that et is non-zero, but I also actually want to assume to start that it's not too large. And this is going to let me apply our expansion. So I'm actually going to assume first that the size of et is between 1 and alpha n. And after I prove that there's a majority violated constraint in this case, I'll prove that this assumption is valid. In other words, that there are never going to be more than alpha n violated coordinates. That this is just impossible, and that will finish the proof. But for now, let's assume that the number of corrupted coordinates is less than or equal to alpha n. So I'm going to define, I'm going to split gamma, I'm going to split the neighborhood of et into 2 parts. It's going to be the union of ut and st, where this is unsatisfied constraints. So remember the neighbors of these, this is kind of neighbors of the left-hand side of the graph. So these are constraints on the right-hand side. And they're either satisfied or unsatisfied by xt. So I'm going to let ut be the unsatisfied constraints, and st will be the satisfied constraints. And notice that if we can prove the following, we'll be done. All we have to do is kind of, to prove that there is a coordinate that has a majority of its constraints violated, all we have to do is kind of sufficiently bound the size of the number of unsatisfied constraints. So these are unsatisfied constraints that touch et. So if we can prove that this is strictly greater than e/2 times the size of et, that means that just by an averaging argument, this would imply, so kind of notice, this would imply that there exists some coordinate in et with greater than e/2 unsatisfied constraints. But each coordinate has e constraints only, right? It's an irregular graph. And so this is equivalent to saying that there exists a coordinate with the majority constraints violated, right? So all we have to prove is this lower bound on the size of ut. And we can do this by the expansion parameter. So in particular, we know, so first of all, we know that the size of ut, so bounding the size of ut alone is maybe a little bit hard, but we can certainly bound the size of ut plus st, because this is just equal to the number of neighbors. right? So this is equal to the size of gamma of ET. But because the size of ET I've restricted to being less than alpha times n, I can apply my bipartite vertex expansion, right? We know that this is greater than or equal to beta times the size of ET. And this is in particular strictly greater than 3e over 4 times the size of ET. Okay, so this isn't quite good enough, right? Because we have this kind of annoying ST term here. So what we need to do is we need to find some relation saying that kind of compared to UT, ST maybe isn't that large. And formally, what do I mean by that? Well, let's kind of compare them by counting the total number of edges. So we know kind of the total number of edges coming out of ET is exactly E times ET, right? Because it's an irregular graph. And I claim that for each unsatisfied constraint on the right-hand side, notice that it has to be hit by one or more edges, right? So if I want to, basically the idea is I'm going to be kind of dividing up the edges. I'm going to be lower bounding them by kind of various versions of UT and ST. So on the one hand, kind of every unsatisfied constraint has to be hit by at least one vertex, right? So we get a UT term. And then the key here is that every satisfied constraint, because we're only looking at constraints that are kind of adjacent to ET, every satisfied constraint has to be hit by at least 2 edges, right? So the size of ST has to be, or rather, sorry, we can plug in 2 times the size of ST here, right? Because every satisfied constraint is hit by at least 2 edges. So the total number of edges, well, you have to at least count for 1 edge for every unsatisfied constraint and 2 edges for every satisfied constraint. And if you just plug 2 into 1, right, this exactly implies that the size of UT is greater than E over 2. Okay, we're very nearly done with this proof. I need like 2 or 3 more minutes. So sorry for going a little bit over. So this implies that this is strictly greater than size of ET, right? And we already said that this, now we're kind of done with step 1. This implies, like we said before, that there is some coordinate in ET where the majority of constraints are violated. So in other words, the algorithm does not terminate. So all we have to do is kind of justify the assumption that size of UT is, size of ET is less than or equal to alpha n. And it turns out that this is actually pretty easy. And the way that you do this is say, well, notice, we're promised that we start with the size of E0 being less than or equal to alpha n over 2, right? This is just by assumption in the theorem. So if there exists a step where ET is greater than alpha n, so let's assume for contradiction there does exist a step where ET is greater than alpha n. This implies there exists some T0 between step 0 and step T, such that the size of ET is actually equal to alpha n, right? To move between alpha n over 2 and something greater than alpha n, and every round we're only flipping 1 coordinate, so we can only move 1 at a time. And this implies that at some point we have to actually hit exactly alpha n. And why does this give us a contradiction? Well, let's just look back at this inequality. So this is still valid, right? Because this was valid for ET between 1 and alpha n, including alpha n. So we have that the size of UT0, the number of violated constraints at step T0, we have that this is strictly greater than E over 2 times alpha n. Why is this a contradiction? Well, we know in every round, the number of unsatisfied constraints strictly decreases, right? Because we're flipping things where the majority is unsatisfied. So every round, we always decrease strictly the number of unsatisfied constraints. And the problem is that U0 at the beginning, well, we're promised that only alpha n over 2 coordinates can be violated at the beginning. And each of these only touch E constraints, right? So at the beginning, we can only start with alpha n E over 2 total violated constraints. And somehow I'm saying, well, I'm always going to decrease the number of violated constraints, but also at some step T0 past the beginning, we've increased the number of violated constraints. We ended up bigger than E alpha n over 2. And this is, of course, a contradiction. Right. So in particular, this implies that this assumption is always valid that we made in step 1. And we already proved that as long as this assumption is valid, when there is still a violated coordinate, i.e. when x is not equal to y, the algorithm will not terminate. So this fully completes the proof. Okay, we're a few minutes over. Sorry about that. But that's pretty much all I wanted to say. On your homework, you'll see, so this gives like an n squared time algorithm for doing this, right? We kind of have to search through for a coordinate that has majority, and we'd only do O of n rounds. On your homework, you'll see kind of a more clever way to do this, where you can kind of simultaneously flip things. That'll be time n log n, and you can even get to linear if you want. This is kind of in the original paper of Sipser and Spielman, so you can take a look there if you're interested. Okay, that's it for today. I guess maybe questions if people want to stick around.
One question: what about vertices that is outside ET?
I mean, they can basically only help us. Right, so we're just looking for a coordinate who the majority of whose constraints are violated, and I'm claiming that you can in fact find one inside ET. Maybe there's also one outside of ET, but it's enough to prove that there's one inside ET, right? So I can kind of just get away with ignoring them.
I just want to ask if you flip the wrong bit, whether it will ruin the process.
No, so it's definitely not true that you'll always flip a bit that is violated, right? I guess there's maybe always a violated bit that you could flip that'll work, but you don't know which one it is, right? So you definitely could end up flipping something that was originally correct, but by what we've proved, you'll always in the end up flipping it back, right? It kind of turns out, in fact, what we proved in the last step is that we actually proved you can't do this too often, right? Because we proved that the number of kind of corrupted coordinates always has to be less than alpha n. So somehow we proved that you can only flip things incorrectly alpha n over 2 time. Like we can never flip too many things incorrectly. That's one way to interpret the last step I did here.
Okay, thank you.
Also notice that the algorithm doesn't know ET. I mean, we don't know ET in the algorithm. We just use it in the analysis.
Right. So there's no, even though there like exists something in ET that would be good to flip, the algorithm doesn't know it. So it absolutely could flip something not in ET. Yeah, the algorithm doesn't know it.
Thanks.
All right, thanks, Max.
Thanks, Max.
Thanks, Max. Have a good weekend.
You too.
And everybody. Yes, I'll stop
Okay.
right there.
Sounds like we can wrap up.